Let's do one more example of dividing polynomials, and we'll do it a little bit faster. So here we have a of x is equal to x to the fourth plus blah, 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 and b of x is equal to x squared plus 3x minus 7. So it's just to compute ax divided by bx. And another thing I wanted to mention is you can take any two polynomials and divide them, assuming that the second polynomial, whatever you're dividing by, has equal or lesser degree than the one that you're starting with. So if you're ever wondering, how do I know if it's going to work or not? That's basically how it's sort of like with numbers, right? If you're going to divide numbers, you typically want to start with a larger number and divide by a smaller number. Now, technically, you can divide a smaller number by a larger number, but it's not going to have a whole component. It's not going to have a quotient. It will be 0. Like, for example, 7 divided by 10. That's 0.7. There is no whole answer. And so you can't, we get a fractional component, but we haven't actually divided it, if you see what I'm saying. We've just changed the representation. Anyways, let's go ahead and get rolling on this one. So we'll start with a, and first one always goes on the inside. So a of x, x to the fourth, plus 3x cubed, minus 16x squared, minus 27x, plus 63. And we are trying to divide by x squared plus 3x minus 7. Neither one of those polynomials had any missing terms, so we don't need to fill in any zeros like we had in the last one. Start by matching. Well, x squared matches with x to the fourth by x squared. Then I need to distribute x squared to the divisor. X squared times x squared is x to the fourth. X squared times 3x is plus 3x cubed. And x squared times negative 7 is negative 7x squared. Now I want to subtract or change the signs and add. So change the sign, change the sign, change the sign, add, cancel, cancel, and this would leave me with negative 9x squared. Be careful with your signs when you're canceling and when you are changing the signs and adding. That's the most common mistake that I've seen students do when they are dividing polynomials. Next, I would be also when you have more than one term canceled, technically that would produce a 0 here. We usually don't, just like I was saying, sometimes we could write the placeholder 0 or not, but basically we're going to skip an x term in the quotient because there was a missing term in this particular position. Because now when I go to match, again, I could drop down the next term. And actually, in this case, we want to drop 2 terms because you can technically drop as many terms as you want at any point in time. But you'll see why I'm dropping both after I do this. But next I would match x squared with negative 9x squared, which would be negative 9 match, because x squared already matches. Now negative 9 times x squared would be negative 9x squared. Negative 9 times 3x would be negative 27x. And then negative 9 times negative 7 would be plus 63. And again, then we would change the signs and add. Change, 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 add. And in this case, we would have, well, negative 9 plus 9, 0, negative 27 plus 27, 0, and 63 minus 63, 0. And in this case, we actually get a remainder of 0. So I wanted to look at an example when we do get a remainder of 0 and talk about kind of what that means. But when we do get a remainder of 0, again, our conclusion is that, well, if I'm doing a of x divided by b of x, that's just equal to the quotient. Basically, this whole polynomial was divisible by this whole polynomial, and the answer that I get through that is just x squared minus 9. Because you could write it as, well, plus the remainder divided by the original divisor, but since the remainder is 0, 0 over anything is just 0, and we get a nice, neat answer. And also, another thing, because division and multiplication are opposite operations in mathematics, another conclusion when we do get a remainder of 0 is that the original polynomial x to the fourth in this whole block is actually comprised of these two pieces multiplying back together. And we'll talk more about this when we get into polynomial factoring, and I don't want to get too much into this right now, but having a 0 remainder means that those polynomials fit back together. Kind of like if I was to do 40 divided by 8, right? Or I guess I'll do 5 because it was similar to the numerical example I used in the last video. That would be exactly 8. And when I get a 0 remainder, basically what that implies is that, well, the answer to 40 divided by 5 is just 8, but at the same time, 8 times 5 multiply back together to be 40. And the same thing is true about polynomials. These two polynomials would multiply back together if you were to FOIL those all out to get the original. And basically, we're learning how polynomials factor. Just like how numbers have factors, 40 factors is 5 times 8, polynomials can be factored using the same exact idea. And there's a lot of different techniques for factoring polynomials. And division is one technique that you can use. It's not as commonly used, but there's a lot of reasons why it can be faster and shorter. In the next video, I'm going to talk about a much faster, easier, shorter way of doing polynomial division, but it only works some of the time. And that's called synthetic division, something that we're going to be using a little bit in Chapter 5, and so it's going to be important going forward.